Okay, so we've learned that arrays are very efficient when it comes to retrieving elements. They're also memory efficient because we don't have to store any extra information with each element in the array. You'll see later on that with many of the other data structures, we can't just store the value. We have to store extra information with the value, but that's not true for arrays. So arrays are efficient when you know the index of the value you want to retrieve, and they're also memory efficient. So let's quickly review here. To retrieve an element from an array, when we have its index, we multiply the size of the element by its index. And remember, every element in the array will have the same size. And multiplying the size of the element by its index gives us the offset from the beginning of the array. And then, of course, we need the start address of the array, and we add the start address to the offset of the element, and boom, we have the memory address of the element. So once again, to get int array 0, if we're starting at address 12, assuming that's our array start address, that would be 12 plus 0 times 4, which is 12. To get 1 would be 12 plus 1 times 4 to get 16, etc. So it doesn't matter how many elements we have in the array. If we have one element in the array, it's going to take us 3 steps to retrieve the element, right? These 3 steps here. Any element in the array. If we have 1,000 elements in the array and we have an index of an element, 3 steps. If we have 100,000 elements in the array and we want to retrieve an element, 3 steps. 1,000,000 elements, 3 steps. 1,000,000,000 elements, 3 steps. And so, as you can see, unlike our adding sugar to your tea example, the number of steps does not change as the number of items changes. So if the number of elements is equal to n, the steps to retrieve never changes. And when we have this situation, we have what's known as constant time complexity, and that's designated by O of 1. And so our adding sugar to tea algorithm had a linear time complexity, which was O of n, because n influenced how many steps were required in a linear fashion. But here, when it comes to retrieving an element from an array, when you have an array index, the number of items in the array has absolutely no effect on the number of steps. The number of steps is always going to be constant. And so this has a constant time complexity, which is O of 1. It means that as the number of items increases, the algorithm doesn't degrade at all. So when it comes to retrieval, one of the advantages of arrays is that retrieving an element, when you have its index, can be done in O of 1 time, which is the best you can get. And so that's one of the advantages of arrays. So let's take a look at some of the disadvantages of arrays. So let's go back to the IDE. So we have our array here, and let's say we read these numbers in from a file or from a database or something. So we don't see this. I mean, this could be anything. And then we have maybe an interface where we let a user type in search values. And let's say the user typed something in, and because of what they typed in, we want to retrieve the number 7 from the array. Now remember, you don't have this information. We're pretending we read values in from a file. We have no idea where integers were added into the array. So somebody comes along now and says, get me number 7 from the array, but I don't know what the index is. So all of a sudden, we can't just go right to the position in the array because we don't know the index for number 7. So what do we have to do? Well, we're going to have to do something like this. I'll change our code here. And instead of printing out, we're going to say if int array I equals 7, then we're done. So I'll say break, but what I'll do here is just say int index equals -1. And then when we find the 7, we'll say index equals I, because that's where the index for 7. And then after the loop, we'll print the index. Let me make some room here. So we're expecting, of course, 3 to be returned. So let's run. And indeed, the index that's returned is 3. But we couldn't just jump to 7 because we had no idea where 7 was in the array. So when we've been talking about retrievals, we've been talking about retrievals when we know what the index is. In this case, we didn't know what the index is. Somebody came along, they didn't say, give me the element at index 3. Instead, they said, give me 7. And that's all they said. Give me the value 7. Get that from the array. And we're like, well, we don't know where it is. So we had to search for it. And so remember, for big O notation, we always consider the worst case. So what would be the worst case for this? Well, the worst case would be that 7 was in the last position in the array. And so the worst case is that we had to search the entire array before we found 7. Now there are 7 items in the array, so n equals 7 for this example, and that means we would have had to have looped n times. And so in this situation, the number of elements does influence how many steps we're going to have to perform. Because if we have 100 items in the array, then in the worst case, we're going to have to loop 100 times. If we have 1,000 items in the array, in the worst case, we're going to have to loop 1,000 times. If we have 1,000,000 items in the array, worst case, 1,000,000 times. So this looks like linear time complexity, right? Because when n is 1, we have to loop once. When n is 10, we have to loop 10 times. When n is 1,000, we have to loop 1,000 times. So it's progressing in a linear manner. And so retrieval, when we know the index, we can do that in O of 1 time. But retrieval, when we do not know the index, the O value for that is O of n, because we have to find the item first, and in the worst case, we'd have to loop over the entire array. So let's go back now to the slides so we can talk about the time complexity for some of the other array operations. Okay, we know that retrieving with an index, we went through this, is constant time. Now we just talked about retrieving an element when we don't know its index. That means we have to search the array, and in the worst case, we have to search the entire array. So the time complexity is linear time. That's similar to the situation we had with putting sugars in the tea. The number of steps increases in a linear fashion as n increases. So let's think about adding an element to a full array. So with our int array, it was already full. So if we came along and for some reason we wanted to add an 8th integer, we can't add it into the array because the array is full. We've learned arrays are not a dynamic data structure. Their length is fixed. So the only way that we could add an integer, another integer, into an array is if we created a brand new array that had a length large enough to take the existing integers and the new integer. So what we'd have to do is create a brand new array and then copy the integers over. And so this would also take linear time because creating the array doesn't depend on the number of elements, and adding the new integer doesn't depend on the number of elements. We just have to know where in the array to add it, so we'd have the index for that. But we have to copy all the existing elements into the new array, which means we're going to have to loop over the entire array. So once again, this is O of n, linear time. Now, if we want to add an element to the end of an array that has space in it, and assuming we know the index of where to add the element, well, that's going to be O to the 1, because that's similar to retrieving an element when we have the index. We can figure out the memory address of where the new element is going to go just by using our simple calculation, and so that's also constant time. And the same thing if we want to insert or update an element at a specific index. We can do that in constant time because if we have the index, we can jump right to the memory location. Now, if we want to delete an element, and we're going to delete it by just setting it to null, or in the case of integers, 0 or -1 or something like that, we can also do that in constant time because all we have to do, if we have the index, is jump right to the memory location. Now, if we did not have the index, I don't have this on the chart, then it would take linear time because we'd have to search for the element first. So if somebody came along and said, delete the number 7 by setting it to -1, we'd have to search through the array first to find the number 7. Now, if we want to delete an element and we don't want to have nulls in our array or placeholders like -1, because that's basically dead space. So what we want to do is when we delete an item in the middle of an array, we want to shift all the other elements down. That's, in the worst case, that will be O of n, because in the worst case, we're going to want to delete the element right at the front of the array. And if we want to shift all the other elements down, we're going to have to loop over all the remaining elements and push them down. So that would be a linear time complexity. So essentially, if we have to loop over the array in any way in order to perform an operation, that's going to have a linear time complexity. If we don't have to loop over the array because we have an index, and so we can just calculate the memory address of the element we want to work on, then that's going to have a constant time complexity. So an easy way for arrays to remember the time complexity is if the code requires a loop, it's going to be linear time. If the code does not require a loop, then it's constant time. Now, I've gone through this fairly quickly because we're talking about arrays, and this isn't a beginner course, so I assume that you know what an array is and you would have some idea of how to code. For example, retrieving an array element when you don't have the index, or deleting an element when you don't have the index by, setting it to null, or adding an element to the end of an array that has space that you would know, that to write the code that keeps track of the last empty position, etc. So I'm not going to code those. And that's all I'm going to touch on for arrays, because this really was meant to be a review. And I want to get into the sort algorithms. Now that we've looked at arrays and we have some idea of the time complexity for these different array operations, we can now get into sort algorithms, and we have a way of comparing how well a sort algorithm performs compared to another one. So I'll see you in the next video.